Hello, good evening, and welcome to the OneClass channel. My name is Fejiro. I'm an honors Bachelor of Science graduate currently working towards medical school. Today I'll be doing my best to go over some commonly asked chemistry questions at both the high school and college levels. If you need some extra homework help or some tutoring or just some further clarification on what was covered today, please check out the links in the description below. That way we can get one of our experts to be able to help you as soon as we can. With that being said, let's kick it off for today with our first question for the evening. And we have for question 1. It says the cyanate ion, OCN, and fulminate ion, CNO, share the same 3 atoms. Okay? So OCN and CNO, they share the same 3 atoms but have vastly different properties. The cyanate ion is stable while the fulminate ion is unstable and forms explosive compounds. So we want to draw the Lewis structure for fulminate ion, including possible resonance forms, and use a formal chart to explain why this is less stable and therefore more reactive than the cyanate ion. So with that being said, I would actually start by drawing the cyanate ion, the best Lewis structure I can think of. So because they have the same thing, we can actually put the same information in. Each one has an oxygen, a carbon, and a nitrogen. So oxygen, based on it being on column 16, has 6 electrons. Carbon, column 14, 4 electrons. And nitrogen, column 15, 5 electrons. When I say this, I mean in regards to their valence electrons. So with that being said, we have 4 plus 5 plus 6 plus this minus here, which counts as 1 electron. Sorry about this. It seems that I'm experiencing a little issue with my pen. So I'll just keep explaining, because what we're going to do here is put in the calculator just to make sure that we have the right amount of electrons for each one. So we should be getting 4 plus 5 plus 6 plus 1 because of the minus right here. Perfect. And with that we have, so it's really just 5 plus 5 plus 6. And yep, 16 electrons each for both forms. And now let's see if we can draw a structure, or at least what we think it would be. So OCN, we have O, C, and N. Just draw one bond between them. Oxygen right now needs one more bond because right now it's sitting as a one unpaired electron. Carbon, 2 unpaired electrons. Nitrogen, 2 unpaired electrons. So there has to be a way to balance this out. The good news is that because there's a minus, actually what we can do is add that probably to the nitrogen side, allowing us then to be able to now form a double bond here and a double bond here, to where we can get O, C, N. Okay? And mind you, this is just one possible Lewis structure. There could be other forms as well for the OCN, but let's check the formal charges. So first we make sure we have 16 electrons. Let's see. We have 4 bonds in total, so that's 8 electrons, and 4 lone pairs, that's another 8. So this is good. For the formal charge, oxygen likes to be like that. That is net charge 0 when it has 2 lone pairs and 2 bonds. Carbon, when they're all bonds. That's its net charge of 0. Nitrogen is only when it has 1 lone pair and 3 bonds. But here, it's replaced a bond with a lone pair. So this nitrogen is currently where the minus will be. Okay? This is a possible Lewis structure for it. Another Lewis structure would be if I shifted a lone pair into a bond of the carbon from the nitrogen and kicked out a bond and turned into a lone pair to the oxygen. So what I'm doing here is this. Now the nitrogen is now its net formal charge is 0, but the oxygen now, because now it's replaced one bond with a lone pair, this is where the minus will be now. So these are both viable forms of this Lewis structure. There's probably more out there, but these ones I would see as the most stable. I'm picturing most likely the oxygen one, where the oxygen has a negative, only because of the electronegativity and the affinity for electrons. I feel like the oxygen is more likely to take on the extra electrons in the nitrogen. But this is what I'm thinking for cyanate, okay? Now, for fulminate, on the other hand, we have CNO, that is the order. So, carbon, now nitrogen is in the middle, and we have the oxygen, okay? So, similar structure, but now the oxygen, same start where it needs one more. The carbon is like that because it needs 3 more, and the nitrogen in the middle is right now sharing 2 of its 5 electrons, so 3, 4, 5. So here an issue already presents itself. How can nitrogen form bonds to where it can satisfy both? For the fulminate ion, it really can't without changing its formal charge. Because as you can see, if I do the same double bond with the nitrogen, and I just send these two over to form that triple bond, even with the carbon, right? And then we also have to add that extra electron, because that's what the 16 would be. What I would end up with is something very similar. And yes, this does work, but you'll see how the formal charges plays a role. So now the carbon has, in a sense, taken the nitrogen role. And you'll see through this picture that it's still going to be a total net charge of just -1. But now we just have more things that aren't 0 compared to the cyanate ion. So here, nitrogen, as we saw, this right here is where it likes to be. But here it replaced a bond. It replaced a lone pair with a bond, meaning that it lost 1 electron as it is now going more positive. So this nitrogen here in the middle is a plus. The oxygen, on the other hand, this one right here is still this form where it's a minus because it now replaced a bond with a lone pair. So we have a plus and minus. So right now we're at 0. But the carbon actually has now also replaced a bond with a lone pair. And this is where our third minus is. We have 2 minuses and 1 plus. And frankly enough, this is one of the best pictures I can draw. I could draw another resonance structure to where, we do the same thing where we move the bonds around. But carbon will always have at least to fill the octet rule, it needs at least 1 lone pair. Because if I try to even move that lone pair towards the middle, I will break the octet rule. So this is an even worse form, but this is also a possible resonance structure. Because now the oxygen here is going to be at 0, because now it's satisfied the 2 bonds and 2 lone pairs. But the carbon, funny enough, is now going to be at 2 minus, because now it's replaced 2 bonds with 2 lone pairs, and the nitrogen is still at the plus. And there's other way I can move this as well, but the point being the carbon just gets more and more of a negative formal charge. These two, as you can see from the cyanate, they're relatively okay. It's not that bad. The nitrogen and the oxygen, although inconvenienced, they're more willing to take on the job because they have higher electronegativity. But in this case here, with the fulminate, the carbon is forced to, even when it doesn't want to. There's no way I can draw this to where I can get the carbon to have even a formal charge of neutral or 0. So this right here should be answering why fulminate ion is less stable and more reactive than the cyanate. Because you can see here, even in my best structure, I still have it to where the formal charges are going off of 0. I don't have any zeros in my formal charges when it comes to these individual ions. And even when I do have a formal charge when it comes to these individual atoms, it comes at the cost of having a greater number of formal charge on something else. So let's see what our colleague says in this case. So what they've drawn here, CNO, this is the fulminate ion. I didn't bother drawing the last one they have here, where carbon is at 3 minus, because at that point, all you're doing is just making the situation worse. Carbon has now literally replaced 3 of its bond with 3 lone pairs, something that it rarely ever wants to do. So I drew the first 2 here, as you can see, where we had the -1, +1, and -1, and the -2, +1 is 0. So even as you're moving things around, it just won't work to where they can get that really nice, stable structure. So, with that being said, they do explain more about the form of charge, and this is why the fulminate ion compared to the cyanate ion is just less stable. Because even in this one, in its worst day, where the nitrogen takes everything and the oxygen has a triple bond, yes, the nitrogen is now at 2 minus and the oxygen is at a plus, but overall, this is still better than what we're getting there, or at least the same type of, I guess, instability. But here, at least we can achieve this form here when it comes to cyanate, while fulminate doesn't have a form like that, to where the formal charges feel at most ease. So with that, this is correct. And I'll say this is more of a conceptual question as well. So we have to really analyze what it means to have formal charges that are near 0. So overall, the more stable a molecule, it's usually related to how many formal charges can be just kept at 0. If it cannot be kept at 0 no matter how you switch it around, that is not a very stable molecule. So let's move on to question number 2. So for this question we have, draw a Lewis structure for the polyatomic phosphite anion, okay? So they want the Lewis structure for PO3 3- as they said there. So, had they not told us that what phosphite looked like, the key thing here is that, remember not to panic, obviously, but the second thing is that if we memorize our 8s, our common 8s that we see, so phosphate, nitrate, carbonate, it becomes easier to approach the ites, because the ites typically are just the 8s but 1 less oxygen, still the same charge, still the same main halogen or anion there, but it's just 1 less oxygen. So phosphate, if you recall, is PO4 3-. So if you take away just 1 oxygen but keep everything the same, that's how you end up with phosphite. And yes, we can still draw a Lewis structure for it, and yes, it will still make sense. It will just be a little bit more haphazard than the phosphate ion. Okay? So with that being said, phosphorus, 15th column, that is going to be 5 electrons. Oxygen, the column right over, 6 electrons, and there's 3 of them, so that's 6 times 3, so that's 18 that it contributes, 5 that it contributes. And when I say this, I'm referring to their valence electrons. And then we have the 3-, so it would be plus 3. So that'd be 5 plus 18 plus 3. And we have 26. Okay? So now, because phosphorus has the most unpaired electrons, we're going to put that one in the middle. Okay? And so we have 1, 2, 3 for the 3 oxygens. Okay? And now we're going to fill out the valence electrons as much as we can. Oxygen right now is sharing one of its 6, so 2, 3, 4, 5, 6. Same thing, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Okay, and phosphorus right now is sharing 3 of its 5, so it's going to be 4, 5. Now, what we cannot forget though are the extra electrons that are added to even stabilize this. So with this being said, actually, funny enough, we're going to have 1, 2, 3. Okay? We're not done quite yet because there's still a bit of work to do, but let's just check now to see if we have the right amount of electrons. So there's 3 bonds, so that's 6 electrons right now, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone pairs. So that's 20 electrons plus the 6 from the bonds. We do indeed have 26 electrons. Now let's check out the formal charges to see if this is a stable, or at least the most stable thing they would prefer. So with phosphite, phosphorus likes to be one lone pair and 3 bonds. That represents a formal charge of 0. Okay? That is its most stable form because that is when the unpaired electrons become bonds. Oxygen, on the other hand, it only has 2 unpaired electrons, so when they become bonds, this will represent its formal charge of 0. But as you can see here, for every oxygen, what happened was that the formal charge is changed because one bond is replaced by a lone pair. When that happens, we become more negative. So each oxygen is actually going to be -1. Which coincidentally is perfect because that's how we end up with the PO3 3-. Each oxygen has a formal charge of -1, which is how this molecule in general has that anionic charge of -3. So theoretically, this would be our Lewis structure for the phosphite anion. The phosphorus really, I could rearrange it, but the phosphorus has no need in this case to take on the negative because oxygen is a more electronegative atom. So it would, if any of them, they would be the ones to prefer to carry the burden of having more electrons, as long as the octet rules are satisfied, which in this case they are. So that being said, that's what they get. So still single bonds, perfect. And yes, everything is just added right there. And this will be the best shape for it. As you can see, each oxygen is where the -1 charge is, and that is how we get the phosphite ion. All right. Let's move on to question number 3. Okay. So, for question 3, we have, what is a pH of a 0.0095 molarity solution of acetic acid, given that the Ka value is that much? So we're given 0.0095 molarity, and they do give us acetic acid, and they give us that the Ka is equal to 1.76 times 10 to the -5. So for this, it's going to take a few steps, but the goal is to find out how much of that acetic acid actually associated to hydronium, so H3O, which represents our acid. So we can just draw a quick formula here. We have HCH3CO2 plus H2O. So that's not going to be factored in because just the solvent. And that turns into CH3CO2 minus, okay, that is our conjugate base, plus H3O, that is water's conjugate acid. So the reason why I drew this out is because what we need here is an ice table. And the ice table is needed because it represents this formula. We have that Ka is equal to the concentration of the products, so that would be CH3CO2 minus times H3O plus over the concentration of the reactants. But the key thing is here is that we do not include the solvents. We don't include like the liquid, which is water in this case. In this case, that's just going to be HC3CO2. Okay? So that's what we have here. And in order to solve for the H3O, that's where we need the ice table, which stands for initial, change, and equilibrium. So bringing it down exactly, we said we were given 0.0095 concentration of acetic acid. And water doesn't count, we can just cross that out. And now for the CH3CO2 minus, the conjugate base of acetic acid, we just assume that we started at 0. And same thing with the hydronium, that we just started at 0. The change based on the formula above will be that for every loss of X here of the acid, these two will gain an X. So what we have here in the formula is 0.0095 minus X, and then we have just X and X here. We can actually use this and plug into our formula to figure out the Ka. Alright, and 5 divided by, just doing a quick math about the Ka relationship with the concentration, because if there's a big enough difference between concentration and the Ka, we can drop the X. So what I'm doing here is finding out if there is a big enough concentration difference. And unfortunately, in this case, there is not. So in this case, we're going to have to apply our quadratic formula. And I'll show you what I mean when I get there. But just as a heads up, what I did was divide the 0.095, well 0095 by the Ka, and the difference was less than 1,000 times greater. We cannot neglect the change that will happen to the concentration of the starting acid. So that being said, we have Ka is equal to x squared, because both these are x's, over 0.0095 minus x. So now we start multiplying across just to be able to now have an equation. We have 0.0095 Ka minus xKa, or Kax, is equal to x squared. And then we move it over and we have x squared plus Kax minus 0.0095 Ka is equal to 0. And here is where we would need our quadratic equation of the negative b. I'll just write it down. We have negative b, well in this case Ka is our b, so negative Ka plus or minus the square root of Ka squared plus, the reason why I say plus, because typically it's minus 4ac, but as you can see here, the c here is a negative value. So it's going to be, and the a is a 1, so that makes it a little bit easier. We have 4 times 0.0095, and the a was 1, but we can't forget the Ka as well, because the whole thing is a c. This whole thing is c. And then divided by 2a. So let's just start plugging it in. I just didn't want to have to keep writing the Ka number. But let's solve first what's under the square root. We have 1.76 times 10 to the negative 5. We're going to square that. And then we're going to do plus 4 times 0.0095 times the Ka value, which is 1.76 times 10 to the negative 5. We get a very small number. Nonetheless, we have to do the square root of it. Okay, still a small number. Not much we can do with it just yet. And then we have negative Ka plus or minus this value. Okay. So now we're going to have a negative Ka plus that. So that's going to be, we're going to assume first is a plus, and we're going to use that Ka value. So plus negative of that. And we get, and then 2a, sorry, don't know why I have a there still. A is 1, so it's just a 2. So we divide by 2, and our first answer is 1, 2, 3, 4. So it's pretty much 4 times 10 to the negative 4 for x. That's our first number that I was able to get. And then the second number, which should make sense, should be a negative, which is something that we don't use. Because when we solve the quadratic equation, most times we end up with one answer that's work and one answer that doesn't, because you cannot produce a negative amount of product. So now we're going to have that same number, put a negative in front of it. Okay. And then we're going to now add that negative Ka. And then divide by 2. And this one we have another answer of 1, 2, 3, 4. 4.18 times 10 to the negative 4, or negative 4.18. So with that being said, based on these two answers, the only one that works is this one. 4 times 10 to the negative 4. That is our theoretical amount of x that's produced. So with that being said, if I plug this in theoretically, if I square this 4, well, 4 times 10 to the negative 4, I should, and then divide that by 0.0095 minus that same number, I should get a Ka of perfect, of the 1.76 times 10 to the negative 5, which I do. So this is a good x to use. So that means x is equal to that But that more importantly means that the concentration of H3O plus is equal to 4 times 10 to the negative 4. So now what does it mean for pH? For this, we have to use our formula of pH is equal to negative log of H3O plus. So let's go ahead and do that. So let's pull back that number. Okay. And negative log of that. And we get that the pH, based on the 4 times 10 to the negative 4, is equal to 3.397 or 3.40. Around there, once we have rounded. Okay? So, that is how I solved for the pH. So the first thing I did was just make sure I had the Ka formula, did my ice table, did the quadratic equation because there wasn't a big enough difference between the concentration, the initial concentration, and the Ka. And then I was able to now find my X and then use the negative log of H3O on it, which I got my pH of 3.40. So see how our colleague did. Ice table, perfect. And then they did the quadratic equation, it seems. They got 4 times 10 to the negative 4. And yep, pH 3.40. So this is correct. So that being said, let's move on to question number 4 for tonight. And we have, what is the Lewis structure for dichlorodiflora-methane? So as you can see in the picture, it's already given to you, but let's see how they got that picture. So we have CCl2F2 Lewis structure. Okay. And before we delve into that, actually, I do want to just review the whole nomenclature and how that big name, dichlorodiflora-methane, just ends up being this. Because you have to remember that methane is just CH4. Okay? This right here is methane. What pretty much this is saying is that we went ahead and replaced every hydrogen with a chlorine or fluorine, and just happened to be 2 of them. So dichloro, difluoro, and still methane, because we still had that carbon in the middle. We just replaced the hydrogens. So that's how they got the name, just as a quick nomenclature review. But let's solve the actual Lewis structure. So carbon, being on the 14th column, has 4 valence electrons, okay? And chlorine and fluorine, being both on the 17th column, each contribute 7 valence electrons each. So 7 times 4, that's 28 in total. And 4 plus 28, that's 32 electrons we're working with. So now let's go ahead and draw this out. We have carbon in the middle, and we have fluorine, fluorine, chlorine, chlorine. And now I'm going to fill in the shells based on their valence electrons. Fluorine right now is sharing 1 of its 7. So it's going to be 2, 3, 4, 5, 6, 7. Same thing here. 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay? And now, with that being said, let's check to see if our formal charges are good. Alright, with that, carbon, I didn't bother to go over how much it was sharing, because as you can see here, it is just sharing 4 of its 4, so it really can't add any more electrons. But if we discuss formal charges, carbon, formal charge of 0 is where it has 4 bonds, which is what this carbon is doing. For chlorine and fluorine, they like to have 3 bonds. Sorry, I always get those 2 mixed up. 3 lone pairs and 1 bond, okay? Which is exactly what each chlorine and fluorine are doing here. So everything here has a formal charge of 0. And now for the last 2 checks, if they check the Octet Rule, and also we have actually 32 electrons. So the Octet Rule, as you can see here, it's good to go. Carbon and the chlorines and the fluorines are satisfied. Now in regards to the electrons, we have 4 bonds, so that's 8 electrons, and then we have 6 times 4 lone pairs, which is 24 electrons. 6 times 4, 3 times 4 lone pairs. I was already counting on the electrons. Well, there's 3 lone pairs on each outer atom, and times 4 of them, so that's 12 lone pairs, so that's 24 electrons. So with that being said, 24 plus the 8 electrons from the bonds, that is indeed 32. So this is our most stable and proper Lewis structure for dichlorodifluoromethane. So this is indeed correct. So now let's move on to question number 5. Okay. For question 5, we have, what is the name of the compound with the formula N2F4? Okay. So N2F4 name. Now this one, it can be a little bit tricky, but the one thing you have to recognize immediately is that this is not an ionic compound. How do we know? Let's look at our periodic table. So according to the periodic table, nitrogen and fluorine are both reactive non-metals, okay? With that being said, this does change our naming quite a bit. We will still have nitrogen and fluorine. The one thing I'll change right away is that just like when we name ionic compounds, we want fluoride, IDE, as the end. But now it comes to what happens in between. For non-ionic compounds, so covalent compounds, typically we want to state the amount of each atom there are in this molecule. And we go through the whole mono, di, tri, tetra, on and on. But that's a key here. We need to state it. So because there's N2F4, we need to say that there's dinitrogen, and we also need to say that there's tetrafluoride. These two are needed for this to be properly named, because that is what covalent compounds do. It also helps distinguish between covalent and ionic, and also because covalent compounds typically are found like this, to where they just have very, I guess, different structures. For example, if I just said it was nitrogen fluoride, it doesn't state how many nitrogens or fluoride there is. In fact, if I was basing off the electrons, I would probably say it was like NF3, because that would probably make the most sense to me. But most of the times, nonmetals don't bond the same way as we do see in regards to ionic compounds, which is why we do have to state how many of them there are, because there's many different versions of a nitrogen and fluoride bond in nature as well. So that being said, let's see what we have. A is just nitrogen fluoride, not enough information. B, dinitrogen fluoride, close, but we need to still state the amount of fluorides we have. C, dinitrogen tetrafluoride, that is what we're looking for. So I'm going to say right away the answer is C. And D, nitrogen tetrafluoride, also close, and may have counted if we only had one nitrogen, because when there's only one atom of the first part of the name, we can get away with dropping the mono, okay? But even then, you still wouldn't be wrong to still just add the mono just to be safe. But in this case, there's still two nitrogens, so we needed that dinitrogen in front, which is why D is not the right answer. So in this case, only one that works is C. Let's see what our colleague says. The name is indeed dinitrogen tetrafluoride. Perfect. So with that being said, let's move on to question number 6. We have, draw the Lewis structure for the nitrate ion, NO3. Assign the formal charge for the central atom nitrogen, and then it's asking what is that formal charge. So with that being said, let's go ahead and write this question down, NO3 minus Lewis. Okay, and then we'll also answer the formal charge of the nitrogen. So nitrogen, being on the 15th column, has 5 valence electrons. Oxygen, being on the 16th column, has 6 valence electrons. So with that being said, we have 5 plus 3 times 6, because there's 3 oxygens. So right now that is 18 plus 5. That is going to be 23. And then we have this nice minus here indicating we're adding an extra electron. So we're working with 24 electrons total. So let's go ahead and draw with nitrogen in the center, not just because the question says so, but also because nitrogen just so happens to have the most unpaired electrons in its atomic form. So we have N, and we have the 3 O's, and supposedly it ends up being 1 minus. So let's just go ahead and now fill in the octets for everything here, or at least attempt to, because right now each oxygen is sharing one of its 6. So 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Okay, let me just reposition this. There we go. And now the nitrogen is sharing 3 of its 5. So we have 4 and 5. So with this being said, there are many ways this can go. But first we want to take care of the issue of the extra electron. For this case, I'm just going to go ahead and give it to one of the oxygens, because typically they would have more of a affinity towards the electron, aka the electronegativity, to where there's no point really of putting it at the nitrogen. And also we're filling an octet rule conveniently. Okay, so there we have it for that. Okay, so that one's taken care of. But we still have at least 2 unpaired electrons. How are we going to approach that? That is a very good question. So for this is where it gets a little bit tricky, because we don't want to break the octet rule. We're going to have to now form a bond with one of the oxygens, and we're just going to literally throw the other electron to the other oxygen. The reason why I say that is because if I try to form a bond with the other oxygen, I'll end up with this shape. And nitrogen, although it would love to, cannot do that, or else it would break the octet rule. So this is a no-no. Can't do that. In this case, when I now form a bond and throw the other one, I still follow the octet rule, and hopefully most things will be satisfied to where they can also follow the octet rule. So now I have this. Okay, so now we're going to see, does it follow the octet rule for everything? Yes, it looks like it does, which is a very good start. Do we have 24 electrons? We have 4 bonds and 3, 6, 7, 8. 8 lone pairs, so that's 16. So 16 plus 8. We do indeed have 24 electrons. Also a good sign. Now what is this formal charge they speak of? So nitrogen, funny enough, for it to have a formal charge of 0, like a net 0, it needs to have 1 lone pair and 3 bonds. This nitrogen here in this picture has 4 bonds. It has replaced a lone pair with a bond. When you do that, when you replace a lone pair with a bond, you become more positive. So this nitrogen actually has a plus. And now you're probably wondering, if this has a plus, how does this whole molecule have a negative charge? Well, let's check the formal charges of the oxygen. Oxygen typically would just be 2 bonds and 2 lone pairs. This is based off of the valence electrons, just in case you were unaware, because nitrogen has 3 unpaired electrons, and that's how it would form 3 bonds. And oxygen only has 2, hence how it only formed 2 bonds. And as you can see, only one oxygen has 2 lone pairs and 2 bonds. The other 2 oxygens have 3 lone pairs and 1 bond. Now we're doing the opposite of the nitrogen. When you replace a bond with a lone pair, you become negative. At least you're taking a negative step in that direction. So with that being said, you can now see that the oxygens, there's 2 negatives and 1 positive, hence how the nitrate ion has that just 1 minus for its ion, this molecular ion. So with that being said, they ask, what is that formal charge for nitrogen? And that's what we just did. We assigned a formal charge, and to the nitrogen is +1 formal charge. Now, mind you, this does have resonance structures to where things do move around, but at the end of the day, most likely nitrogen will remain that +1 because there's no way we can reorganize it to where nitrogen becomes neutral and it doesn't break the octet rule because it needs to be able to form those bonds with the other oxygens on the extremities, okay? And if I were to move certain things out, then it's no longer following the octet rule. So that being said, this is what they got. Perfect, that's the picture we have right now. 2 negatives, 1 positive, and the formal charge of nitrogen is indeed +1. So this is perfect. So move on to now question number 7. We have, how do phospholipids interact with water molecules? So, with that being said, phospholipid, the one I think of, at least when they mention this, I think of the phospholipid bilayer. This is when it refers to cells, specifically, I guess animal cells will have this. And the phospholipid bilayer kind of looks like this. There's the, as I said, the polar head and the hydrophobic tail. And the reason I call it bilayer is because then we have the other side, where the hydrophobic parts point inwards. Sorry, let me see if I can redraw that. So in a sense, it just keeps going around, and this is kind of like what the what they refer to as a phospholipid bilayer for cells. Okay, we have a polar outside and a non-polar inside. Okay. And that's the best thing I think of when it comes to phospholipid bilayer. And it's because I remember this is how I can tell how it interacts with molecules. And like I said, this will be the head and this will be the tail of it. Okay? So now let's see what each answer says. It says a hydrophilic head avoids water. The hydrophobic tails attract water. So here, it's actually giving us a lot of information. They say hydrophilic. Now when it says philic, it means loving. So hydrophilic means water loving. There's no way a water loving something will avoid water. So you can already guess based on this what the next part will say. It says a hydrophilic head interacts with water while the hydrophobic tail avoids water. Hydrophobic kind of translates to, water fearing, okay, and it's just another way of saying that it doesn't want to interact with it. So what's happening this now, the way you think about it is that for the phospholipid bilayer, we have like polar stuff on the outside and stuff like that, and it's able to now, I guess, hold its shape because the water-loving side interacts with it, but the water, I guess, avoiding side doesn't let things just easily pass through. You need to be a very small solute or something to pass through a phospholipid bilayer, because typically if you're polar, you're not going to get through the tail part. Okay, with that being said, B is currently looking like the best choice. And now for C, it says phospholipids do not interact with water because water is polar and lipids are non-polar. So funny enough, C is also very wrong because phospholipids specifically is that phosphorus part that serves as its polar head part, and the lipid that extends out of it is the non-polar tail. So to say that lipids are non-polar technically isn't incorrect, but phospholipid is a combination of a polar and a non-polar side. With all that being said, the best choice is indeed B, because it says that the hydrophilic head, which is where the phosphorus and stuff is, interacts with water, while the hydrophobic tail, which is where all the lipids and the fats are, avoid water, which is typically what you see in the phospholipid bilayer. Okay, so with that being said, they say the answer choice is indeed B. Phospholipids is able to interact with water because of the hydrophilic head, but the parts that don't want to attract water are the hydrophobic tails, which is a long chain of hydrocarbon of fatty acids. So this is correct. So question number 8. For question 8, we have draw the Lewis structure of CH2O2, which is going to be frankly tricky, but we're going to try anyways. So, with this being said, we're going to have to think about what this means, because there's many ways to draw CH2O2. We have to think of a way that'll be able to really balance this out. So, we have H2O2 Lewis. Okay, so carbon, 14th column, 4 valence electrons. Hydrogen, the first column, it only has 1 valence electron, but there's 2 of them, so that's 2. Oxygen, there's 2 of them, but it's on the 16th column, so that's 6 valence electrons each, so that's 12. So 4 plus 2 plus 12, we're working with 18 electrons. So, with that being said, we're going to need to, I believe, start with this and then move things around until something works. I have an idea in my head right now of what might work, but it's important to take it step by step, just be able to see the mental process. So, carbon in the center, filling in the oxygens, because it was sharing one of its 6, so it looks like that right now. Incomplete octet. Same with this one. And the hydrogens are fine. The carbon as well is already sharing 4 of its 4. So how do we take care of this situation here? I don't know, because this right here is not going to work. And the oxygens wouldn't form a bond with each other. It wouldn't end up doing like this. Although this sounds like a nice idea, it's rarely seen unless specified even in the question, because there are a lot of situations in the real world where molecules do form like these type of shapes, like for example benzene and stuff, and just cycloalkenes or alkynes and alkanes. But overall though, we want to avoid doing something like that. So then how do we take care of these 2 unpaired electrons? We really can't. So I propose we draw something else. We would draw maybe this, COH. Why did I draw this? Because as we balance this, we might be able to solve our issue. So, and also the reason why I do this wasn't just out of random chance. I know hydroxide, OH-, is indeed a thing that likes to float around. So maybe by including a hydroxide here, I might be able to find a way to balance this out. So the same thing, we have 1, 2, 3, 4, 5 of the 6, and 1, 2, 3, 4 of the 6. Because in this oxygen, it's already sharing 2 of its 6. So this is fine. But now the carbon actually is sharing 3 of its 4. So the 4th one's right there. And now finally we have a situation to where actually it's okay to put these bonds here, because we're not breaking any octet rules. We're not having an awkward situation where we have to bond like a triangle. This can work. So we have now this. And funny enough, I think this is methanoic acid, but that's a different conversation. This is a possible thing that can work. But let's double check with our total electrons and formal charges, and if they all follow the octet rules, at least the ones that can. So we want 18 electrons. We right now, I can count 1, 2, 3, 4, 5 bonds. That's 10 electrons so far, and I see 1, 2, 3, 4 lone pairs, so that's 8 electrons. So this does indeed have 18 electrons. Great start. And now, with that being said, does it follow the octet rules for the ones that can? Yes, it does. Formal charges. Carbon likes to just have 4 bonds to be a formal charge of 0, which is what it's doing here. The double bond just counts as 2 bonds. So that's good. Oxygen, on the other hand, likes 2 bonds and 2 lone pairs, which both oxygens are doing, which is also great. The hydrogen just likes to have 1 bond, which is also what it's doing. So all these I've drawn out on the side are just formal charges of 0 for each atom, which is what each atom here is doing. And so this would be the best Lewis structure right here for CH2O2. Now, as I said, I do believe this is methanoic acid because this has the, if I rewrote this, it'd be HCOOH, which is usually the way you write it to imply that it's methanoic acid. With that being said, let's see how we did based on our colleague. Yep, they went right to draw like that, which is perfect. And then they drew it at first like this, but then they made it into the double bond to complete the octet. And this is perfect. This is correct. This would be the Lewis structure for it. So the lesson here really is that I think I was only able to find out because I was familiar with the other possible combinations of molecules I've seen. So I was able to identify a hydroxide and rearrange it as such like that. With this, it is important that you can do that because as I first approached it, seeing that carbon had the most unpaired electrons, you almost force you to put everything around carbon. But sometimes, as you see here, it's just not possible. So it's good to try to rearrange things, but aim to rearrange things in familiar things that you've seen before. Okay? So question number 9. So for question 9, we have, how would you name blank? There we are. So we have HBr04, KIO3, NaBrO2, and HIO. So that IO is definitely going to be one of the trickier ones. And because I don't have all of these memorized, I'm definitely going to have to refer to a sheet. But with that being said, HBrO4, as they show here, one of my colleagues that I'm just going to refer to, I do see the beginning of it. It actually is a good idea to separate these by their anions and cations. So we have KIO3, NaBrO2, and HIO. Okay? So with that being said, HBr4 is a hydrogen and BrO4. Okay? And I do actually conveniently have a list of ions we can refer to. Okay? Polyatomic ions. As soon as that loads, because this would be H and Br4 minus. We have K plus and IO3 minus. We have, just make sure everything is, yep, we have Na plus and Br02 minus. And then we have H plus and IO minus. So with that being said, let's see what we can find on our polyatomic ions list. So lucky for us, they were able to give us this nicely organized list of different ions. But unfortunately, it does not tell us about the ones we're looking for. So that's going to be a slight issue. But maybe we can find out what the name is based on the information we've been given through here. So that answer is no. We may have to refer to our acid sheet. Nice. So we have iodic, there we go, hypoiodous. But that just gives us a name, unfortunately. I would like to find out what just this IO minus is. So with that, we're actually going to refer to our colleague here because I am not familiar with the names of these ions. And with this, we're going to try to construct a way to learn how to name these ions. So perbromate, perfect way to start. Because I know BrO3, if I remember correctly, hopefully, should be, is there even a BrO3? Is there a bromate? There it is. Thank you. So bromate, BrO3. So there's different names. We have an 8 ending, which is considered the full ending. Then we have something that goes above it, where we have the per prefix and then the 8 ending still. Okay, and 8 means, I mean the per in this case means that we add, so it's plus 1 oxygen. So here's a neutral side, all right? And then we have a step down where it's called the ites, okay? And that one is minus 1 oxygen. And based on this, if my theory is correct, I think when we do another step down where it's minus 2 oxygen, it has now hypo as a prefix, but it's still ite. So with that being said, let's see here. IO3 is iodate, perfect. BrO2, because I know BrO4 is perbromate, you can see how BrO2 is bromite. And now, this is indeed hypoiodite. So this is perfect. Unfortunately though, this rule is when it comes to the ions. How can we now translate that rule to when it comes to the actual, I guess, not only acids, or when it comes to when they're bonded with other things? So, with that being said, if we're dealing with acids, okay, still the same-ish rules. Instead of an 8, we start at ic acid. Okay, we replace the 8 with ic acid. That's a neutral. And when it's one less, it's us acid. So like hypochlorous acid, for example, instead of hypochloric. Pretty sure I named something else. Instead of chloric acid, which is like ClO3, we have chlorous acid, which is like ClO2. Now, if it was, sorry, this shouldn't be black. This should be, if it went down, this is minus 1 oxygen. Goes down again. What is minus 2 oxygen? And what is plus 1 oxygen? Okay, that is the name we're trying to figure out now. When we do that, based on our acids sheet, if we look at ClO4, HClO4, which is perchloric acid, it seems to stick with the same prefix of the per, but instead it has the ic acid, okay? And if we look at this and we look at HIO all the way down here that I spotted earlier, nope, went too far down. HIO. Well, actually, you know, HCl works perfectly fine in this case as well, because it says hypochlorous. So it looks like it still keeps the hypo, and it's still the OUS, but you still had acid. So these are the two rules I would actually try to abide by based on these molecules. So when you're dealing with things that aren't acids, you refer to this side here, the red. Okay, so let's actually answer the first question. We're given HBrO4. So that is now adding an acid, the proton, hydrogen, right, to BrO4. So we're going to refer over to this side, and that would be perbromic acid, it looks like. That would be the name. Okay? K and then IO3. So this is now potassium, but we're going to refer to the red side now. Okay? This would be a potassium, and IO3 is just the 8. That is the stable. And that's the tricky part here. You have to recognize it's not always a distribution of 4 and 3, or like it's not always going to be 3s or neutral. A great example is phosphoric acid. It's H3PO4. The important thing is that phosphate ions are PO4. That is their base. So like if it was possible, per phosphate ion would be like PO5 if it was possible, and a trying to make sure I have the right word, phosphite ion, which I do see, is PO3. Point being is that the 3 or the 4 on the oxygen, they depend on what it's attached to. So I'll go and memorize the 8s, and then I would use this sheet to then figure out, okay, which one are they talking about? Because once you memorize your 8 and know what the amount of oxygens they have there, when you see different types or different numbers of oxygen, you can tell yourself which way to go up or down in regards to the name. So back to this would be potassium iodate, okay, because IO3 is the 8. And now BrO2, that one I remember, as we saw, I think, bromate is BrO3. So this is now bromide. So this would be sodium bromide, okay, because this is still referring to the red side. Now, which is the acid, we have HIO. And this one, even though we did find out on this sheet as well, we can actually say it would be hypoiodous acid, because it's lost 2 oxygens, because it used to be IO3. And I was sure I saw it on this sheet. There it is. Hypoiodous. That is the acid name. So let's see what our colleague did. So thank you again for him to actually be able to provide this. Potassium iodate and sodium bromide, we got those correct. And now for the name, we have perbromic acid, perfect, and hypoiodous acid. And that is what we should get. Perbromic, potassium iodate, sodium bromide, and hypoiodous acid. If you want to take a quick snippet of this table, I do believe it can come in handy when you do try to solve type of questions. And I do stress that you have to memorize your 8s and your ick. Once you know what the base is, just what oxygens they're supposed to have, when they have more or less, you can use this table to navigate that name. So now, back to what we were doing. Question number 10. We have draw a Lewis structure. We want the number of valence electrons, and we want the formal charge. So we have BH4 minus. So that's boron and 4 hydrogens. So funny enough, boron is on the 13th column, so that'll be 3 electrons. And hydrogen is on the first column, so that's going to be 1 electron each times 4. So that's 3 plus 4. And this nice negative means we add 1 more. So we're dealing with 8 electrons total. So let's just go ahead and draw this out. We have B, 2, 3, 8 electrons, 4. How does boron do something like this? This is a great question, because typically boron only has space for 3 hydrogens. So right here, in fact, I literally cannot make any changes. What I can do is say how many valence electrons and what is the formal charge of this. So with that being said, how many valence electrons does each one have? I kind of scribbled it up here. Boron contributes 3, hydrogen contributes 1 each. But what is a formal charge here? The formal charge for hydrogens, when it just has 1 bond, that means it's going to be a charge of 0. So all the hydrogens have a charge of 0. Boron, on the other hand, because it typically has 3 valence electrons, this would be a net charge of 0 here. But as you can see here, that's not what the boron is doing. The boron has 1 more extra bond. So when you add a bond, and this is a difference, when you're adding the bond, not replacing lone pair, but just adding another bond, that right there also sets your formal charge to a minus. You've now taken a step towards a negative. So this boron here is actually going to be a minus. This is where the formal charge, I guess the negative charge is for the boron tetrahydrogen, or however you call this. That is where the negative is going to be for this to be a negative ion. Okay, this would be how you draw that Lewis structure, and the formal charge for boron is -1 formal charge. Okay, so we have 3, 1, 1, so 8 in total, which is perfect. That's also what we have here, because we only have 4 bonds, that's 8 electrons. So then they drew the Lewis structure, bam, and there you have it. The boron is where the formal charge minus is. All the hydrogens are perfectly at peace. So the Lewis structure is just that. So now, with that being said, let's take a quick mini break to see how the stream is doing. So far, so good. Oh, whoops. Sorry about that. Should have done this instead. Okay. Everything's looking good. Our audio is good. All right, perfect. I just like to check in every hour just to be able to make sure. Now we can move on safely to question number 11. Hopefully this thing changed. Let me just double check. Okay. So yep, let's move on to question 11. We have, what is the molar mass of cobalt-3 nitrate? Okay. And how many oxygen atoms are there? There's 4.25 grams of cobalt-3 nitrate. So right away, this is really bothering me, and I'm glad my colleague addressed it, because cobalt-3 nitrate should be CONO3, not 2, because nitrate ions, NO3, are just 1 minus. Cobalt-3 is implying that it has a 3 plus. For these to cancel out and balance, you need 3 nitrates. So I'm glad my colleague, as he shows there, is dealing with cobalt-3 nitrates in its true form. So let's go on like that as well. So we want to find out first the molar mass of cobalt-3 nitrate, okay? So we want to add up the constituents. So we have 1 cobalt, and now we're going to multiply 3 into each part there. So we have 3 nitrogen, and we have 9 whole oxygen, okay? So now we got to refer to the periodic table to see how much each weighs in their atomic mass units. Cobalt is right here. Element number 27, 58.933. Nitrogen is element number 7, 14.007. And there's 9 whole oxygens, which each weigh 15.999. Okay, so that is 58.933. Whoops, sorry, that's not what I want to do. Because 1 times that, we're going to have the same number. I don't want to add just yet. 58.933. Perfect. And then this is where we want to multiply first. So 14.007 times 3. 42.021. And then the last one we have 15.999 times 9. 143.991. I'm going to add it all together. Plus 58.933. So the total we should get for the molar mass is 244.945. And the most important part you cannot forget is the units, which is grams per mole. So this should be the molar mass that we get. Okay? So with that being said, it's also asking how many oxygen atoms are there in 4.525 grams of cobalt-3 nitrate. So now we want to find out how many moles are there in that 4.525 grams, and then we're going to use Avogadro's number to find out how many atoms of oxygen are there. But before we even go there, we need to first find out how many moles of oxygen per 1 mole of cobalt, which should be a 9:1 ratio, as we've done here. well, to be specific, 1 mole of this molecule. So with that being said, we have 4.525 grams. And we want to convert it to moles. So we're going to have to do this. 244.945 grams for every 1 mole of the cobalt NO3. And now for every 1 mole of cobalt NO3, we have 9 moles of oxygen, because as it shows here, 9 of O. And now, this is where we factor in Avogadro's number. For every 1 mole of any element, but in this case is oxygen, we have 6.022 times 10 to the 23rd atoms. So there's going to be a lot of crossing out just to make sure we end up with the right unit, atoms of O. So grams, moles of cobalt NO3, cancel out with that, moles of oxygen with moles of oxygen, and that's all we're left with, atoms of oxygen. So we have 4.525 divided by that molar mass times 9 times 6.022 times 10 to the 23rd. We get, there should be 1.00 times 10 to the 23rd oxygen atoms, based on what the calculator is saying. Hopefully with this we're able to actually cancel the right units, but let's see what our colleague was able to do. So they did get the molar mass was 244.93, which is close to what we got. It just depends on the periodic table you're using. As you can see, their values slightly different from mine. Okay, and then we found the moles. Well, that's what they did, 0.01847. Then they multiply that by 9, because there's 9 moles of oxygen atoms, and they got this 0.1662. Then they used Avogadro's number, perfect, and they got 1.001, which is actually what I got. I just wanted to round up a little bit earlier, but exactly, they should. I'm just trying to check the original question. I see. So that's why you should round to 1.001, because the original number was 4.525, which had 4 significant digits. So I will just add that. And yep, my calculator is 1.001 as well. So there are indeed 1.001 times 10 to the 23rd oxygen atoms. So this is correct. Now for question number 12, we have calculate the molar mass of CH3CH2OH. Funny enough, this is ethanol, because that's ethane, CH3 is ethane, and when you substitute one hydrogen with a hydroxide, that is how you make alcohol. So that's ethanol. So with that being said, though, we want to find the molar mass based on the constituents. So we still follow the same rules, okay? We have 2 carbons, and then we have 6, not oxygens, 6 hydrogens, and 1 oxygen. So that's 12.001, 6 hydrogen, that's 1.008, and 15.999. So that's 24.002 that carbons contribute. This is 6 times 0.48 for the hydrogens, and this stays the same at 15.999. And then we're going to add it all together. 15.999 plus 6.048 plus 24.002, and we get 46.049. And we cannot forget our units. It's always going to be grams per mole. So yes, we added up the constituents, which are the atomic mass units of each atom present in this molecule. Let's see how our colleague did. They have 2, 6, and 1, perfect. 12, 6, 16, and they add up to 46 grams per mole. So the answer is indeed, well, I guess D in this case, the 46 grams per mole. So this is correct. Now let's move to question number 13. We have SeF6 has an expanded octet around selenium. Draw the Lewis structure of this molecule. So SeF6 Lewis structure. Okay? So right away, we know it has an expanded octet based on what it said. Okay? So selenium, I do believe, is on the 16th column. Let me check the periodic table. Yes, it is. 16th column, so that's 6 valence electrons. Fluorine, on the other hand, 17th column right next to it, 7 valence electrons, but there's 6 of them, so 7 times 6, that is 42, plus another 6 from selenium, so we have 48 electrons total we want to distribute. So right now we're just going to put selenium in the middle, and as it says, it has an expanded octet, so this is all fair game. We're just going to draw whatever we can to be able to make this fit. So we have 1, 2, 3, 4, 5, 6. So F, 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 F. And now let's add the leftover, not lone pairs, but the leftover valence electrons. So fluorine right now, each of them is sharing one of their 7. So theoretically, each of them should fill their octet rule because it should be 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Sorry, that one didn't look so together. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. So we have here SeF6. Are we done yet? Unfortunately not. Let's see first if we actually do have 48 electrons. So right now we have 6 bonds, so that's 12 electrons. And on each fluorine there's 3 lone pairs and there's 6 fluorines. So 3 times 6, that is 18 lone pairs. And we double that for the electrons, we get 36. So 36 plus 12, perfect, that is indeed 48. So we're good with that. Now let's see if we can do anything about their formal charge, or at least let's see if the formal charges of this whole thing is indeed 0. We have for fluorine, it likes to have 3 lone pairs and 1 bond. That is what a formal charge of 0 looks like for fluorine. And in this case, that is what every fluorine is doing here. Selenium, on the other hand, likes to actually have 2 lone pairs and 2 bonds. So then how the heck can it do that? In this case, having a lone pair can be switched to having 2 bonds and you would still have the same formal charge. What do I mean? If I did this, we still have a net formal charge of 0 on the selenium. That is still 0. But now we can say it has 6 bonds. Okay? And this only works typically with those that can actually expand their octet rule. So selenium also has a formal charge of 0. So this actually would be the Lewis dot diagram for selenium hexafluoride. Okay? So let's see what they get. Yep, that is the answer right there. And everything else is good. So this is correct. So now let's move to question number 14. What is the Lewis structure of xenon dichloride? So, xenon dichloride Lewis structure. So with this, xenon is actually on the 18th column. I can say right away it's going to have an expanded octet, because this is one of the noble gases, or these noble atoms, and they don't even want to form bonds. So the fact that they are, it's anything goes. Well, reasonably anything goes, at least for the xenon. And the chlorine still should follow the octet rules in this case. Nonetheless, we have xenon, which contributes 8 valence electrons, and chlorine, which is 7 each, that's 14. So in total, we're working with 22 electrons. So we're going to put xenon in the middle because it's the only unique one, even though technically it has 0 unpaired electrons. Nonetheless, let's see what we can do here. We're going to have 1 chlorine, 1 chlorine. Fill in the octet for the chlorine because it was sharing 1 of its 7, which is why I was able to add 6 more. Same here, 2, 3, 4, 5, 6, 7. So that's very nice. Xenon, on the other hand, is right now sharing 2 of its 8. So it's going to be 3, 4, 5, 6, 7, 8. That right there would be xenon dichloride. Now we're going to check to see if we actually have 22 electrons. 2 bonds, so 4 electrons there. And we have 3, 6, 9 lone pairs. 9 lone pairs, that's 18 electrons plus 4 from the bonds. We do indeed have 22 electrons total. Do these abide by like a formal charge of 0? So chlorine, for it to have a 0 formal charge, likes to have 3 bonds, 3 lone pairs, and 1 bond, which is what each chlorine has. The xenon, on the other hand, likes to have, unfortunately, 4 lone pairs, 0 bonds. So then how can we compare these two? The cool thing is that when you turn a lone pair into 2 bonds, you keep the same formal charge. So I can do this. So now I can say xenon can have 2 bonds and 3 lone pairs for it to have a formal charge of 0, which is what it's doing here, which is why this would be the best structure for xenon dichloride. This is indeed the lowest structure for it. Let's see what our colleague says. 22 electrons, and there we go, right here. 3 lone pairs in the xenon and 2 bonds sticking out of it. So now for question number 15. We have draw all the resonance structures for carbonate ion, and I wish that I did not see that because now I know I only have to draw 3. But nonetheless, let's see if we could have figured out how many resonance structures it would have. So the goal here, I like to do personally, is just draw the best resonance structure based on its formal charges. So we're aiming for a carbonate, okay? So carbon being on the 14th column has 4 valence electrons. Oxygen, 16th column, 6 valence electrons. There's 3 of them, so that's 18 it contributes, plus the 4 from the carbon, and plus this nice 2 here because of the fact that there's 2 extra added electrons. So that is, in total, 18 plus 4 plus 2. We're dealing with 24 electrons total. So with that being said, we're going to put carbon right in the middle, and we're going to now add the oxygens. And now we're going to try to fill in the rest of the valence electrons based on what it has left. Oxygen right now is sharing 1 of its 6, so 2, 3, 4, 5, 6. Same thing here, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. And now what I'm going to do is go ahead and add the 2, sorry, not just yet, sorry about that. Went a little too far ahead because carbon right now is sharing 3 of its 4. So we need a 4th one right there. Now what I'm going to do is go ahead and add the 2 extra electrons, 1 right here and 1 right there, just to fill in those 2 octets. And now for the last one, I'm actually just going to create a double bond here. Okay? So now we have, this would be 1 of its 3. Okay? this. And every octet rule should be filled for each one. And now let's check their formal charges to see why this would even count as a resonance structure. So for carbon, it likes to just have 4 bonds for it to have a formal charge of 0. So that carbon in the middle is perfectly content. The double bond counts as 2 bonds. For the oxygen, for it to have a formal charge of 0, it needs to have 2 bonds and 2 lone pairs. Only one oxygen does that. The other 2 oxygens have gone ahead to replace a bond with a lone pair. When you do that, you become more negative. You've now taken a negative step. So each oxygen here is a formal charge of -1. And as you can see, it makes sense because the whole molecule has 2 minus for its charge. This is where it's coming from. And just before we go any further, we're going to actually see if we even have 24 electrons. So we have 4 bonds right here, so that's 8 electrons. And we have 3, 6, 7, 8. So that's 8 lone pairs times 2 is 16, plus another 8, 24. Perfect. So this is one of the 3. And why am I now so confident that there's 3? Is because think of these oxygens as separate entities. What if the middle one wants a double bond? Which is exactly, funny enough, what we're drawing. This counts as a different molecule, technically, or at least different resonance structure than the one on the left. Because now different oxygens have the formal charge of that -1. It's going to be this oxygen here, this oxygen there. This is a possible resonance structure. And now you're probably guessing, okay, then that means the last one you can draw is now when the double bond is all the way on the left now, which is what we're going to draw. Okay, this would also be a different resonance structure because now we have the formal charges on the left, on the right, and on the middle carbon. So this is now the 3 resonance structures, at least I can think of, when they say they have 3, because each time the double bond is moving to a different location. Okay? So let's see what our colleague has to say in terms of the rest for this carbonate ion. Yes, so as you can see, we have the 2 minus here at the bottom, then it shifts where the double bond is now on the left, so the 2 minus is here. And now it shifts again to where now the double bond is at this bottom one here, and we have the 2 oops, looks like they may have drawn this a little bit off, because this is correct, yes, but they forgot to get rid of the minus here and the minus here, because this would not be it. I'm going to say that this is incorrect, only because it's mistakes like these, especially when you're using like a software that you're given to by like your school and stuff. It's very important to double check your work and make sure that you have gotten rid of certain signs and everything, because this is, for example, is telling me that I have CO3 3 minus, and doesn't even say where we even got the minus from, because that's a neutral formal charge. This right here is a neutral formal charge. There should not be a negative there. So it's just stressing the importance of checking over your work to make sure that your formal charges are indeed what they should be. Okay? So for this is asking us, for this question, what is the magnesium fluoride formula? So unfortunately, you can probably already see the answer there. Can't really hide it. So with that being said, we'll refer to our nice and handy periodic table, because we want to see what type of molecule this is. The type of molecule does affect how we're going to write it down based on the name. So magnesium fluoride looks like it has a magnesium and a fluorine. But the key thing is here is that magnesium is a metal and fluorine is a non-metal. So with that being said, we would need to consider their charges when they're ions. Okay? So magnesium has +2 as its ion because it's on the second column and usually just gets rid of 2 electrons in order to achieve its noble gas state. Fluorine, on the other hand, needs a -1 as an anion for it to reach its noble gas state. So how do you balance it? We need 2 of these fluorines, okay? So in order for this to work, we need MgF2. This right here would be the magnesium fluoride formula. So let's compare now here. Exactly, that's what our colleague says. MgF2. So now question number 17. We have, what is the Lewis structure of HSO4-, and they've done it again so we can just see it. So with that being said, I'm glad they have HSO4- because, let me just write the question down first. We can actually say that what we're working with is an SO42- polyatomic anion. This is a sulfate anion. The reason why I wrote it like this first is because actually, for me at least, it helps me write things out appropriately. Because when I write it out this way, I avoid the mistake of putting the hydrogen on the sulfur. And I know you can see the picture here, and you can see how the oxygen is where the hydrogen attaches to. I will show you why that happens by first drawing the Lewis structure of a sulfate anion, okay? So with that being said, sulfur and oxygen are both on the 16th column, so that's 6 electrons, so that'd be 6 times 5, that's 30, and then plus that 2, because there's 2 more based on this here, it's going to be 32 electrons we're working with, okay? So we have the sulfur is going to be in the middle, as you can see in this picture. All right, we're going to first start with 1 bond here on each side, 4 oxygens, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and just that instead. And then for the sulfur, it's right now sharing 4 of its 6, so it's going to be 4, 5, okay? And now I'm going to just freely throw in the extra negative from the sulfate ions, that's 2-. I'm going to go ahead and balance maybe this one and this one, okay? So I do want to kind of mimic what the picture is doing. And so here, in order to quote unquote get rid of the unpaired electrons, we're going to form bonds. And sulfate or sulfur does break the octet rule, which is why this is allowed. And so we get this. Let me draw it in blue. S, double bond on each side. The oxygens up here. And then these like that. And then this oxygen down here. So this would be a sulfate anion, okay? And now, when we do the formal charge, for sulfur, it likes to have 2 lone pairs and 2 bonds. But it can also be expanded to where you turn every lone pair into 2 bonds, to where you can say, oh, sulfur also likes to just have 6 bonds, which is what the sulfur in the middle is doing. The double bonds count as 2 bonds each. So now, with oxygen, it likes to have also 2 bonds and 2 lone pairs, but it can't really expand like sulfur. But let's compare what's happening here. These 2 oxygens on the left and right follow that, okay? But the top and the bottom have gone ahead to replace a bond with a lone pair. When you do that, you actually become more negative. In terms of your formal charge, you've taken a step in the negative direction. That is what sulfate looks like. So now, when a hydrogen comes in, typically we just see the H plus minding its own business. Where would the H plus want to go? Any of these oxygens. It can go to the top one or the bottom one. Point being is that overall the H plus will be attracted to the negative side when it comes to the formal charges of this molecule. So I'm going to go ahead and just draw it be attached to over here, just like we have in that picture. And that's how we got hydrogen sulfate ion for this molecule. Because had I just gone straight to draw it, I may have tried to squeeze the hydrogen on the sulfur, which is why I like to draw what I know first, which is a sulfate. And then I just added the hydrogen onto it. So with that, once you had the hydrogen onto it, you can see now this is how we got rid of that formal charge. Because this was an H+, which is why I was able to just stick right on there. And now only, I guess, formal charge that's left of negative is up here. Hence how the whole thing is just 1 minus. And yes, when you do have sulfuric acid, H2SO4, that is because another hydrogen has come and taken care of that other negative formal charge. So now, time for question number 18. What is a Lewis structure for each atom or anion? So we're literally given at certain points some atoms, some anions. So we have S2, oh, that's going to be a little bit tricky. S2 minus. We have B, just a magnesium. We have C, now a simplified magnesium, Mg2 plus. And then we have D. We have phosphorus. Okay. So, that being said, we're going to start from the beginning. We have the S2 minus. So 2 sulfurs. Sulfur is on the 16th column. That's 6 valence electrons, and there's 2 of them. So that's going to be, this is going to be quite a hard one to draw. I'm just trying to picture because we have S2 minus. So unfortunately, we're going to have to deal with 13 electrons. An uneven number is already a good foreshadowing of the stress that might be caused. And I think I know what it might be saying now, actually, embarrassingly enough. I think it may have been miswritten. We actually want to do S2 minus like that. We're not getting 2 sulfurs. It's 1 sulfur with a charge of 2 minus. So sulfur, as we said, 6 valence electrons originally. Okay, so we have 1, 2, 3, 4, 5, 6. And if it's 2 minus, we're adding 2 more electrons. So 7 and 8. This right here is S2 minus. Magnesium, just by itself, has 2 valence electrons. So that's M, G, and 1, 2. This will be magnesium. 2 plus, funny enough, would just be Mg. And 2 plus on the outside. That's all we need to do because we got rid of the 2 electrons. Now phosphorus, the Lewis structure for this would be, because it has 5 valence electrons, due to it being on column 15, it'd just be 1, 2, 3, 4, 5. That would be it for phosphorus. So as you can see here, it has 3 unpaired electrons in its Lewis structure. So with that being said, let's see what our colleague has to say. There wasn't much we can do here. Hopefully they can shine some light. So this is what they have for the S2 minus, and that one is interesting because this, if anything, would be S2 2 minus. So if that's what they're asking for, sure. For B, they just have Mg with the 2 electrons. For C, it's just Mg 2 plus, as we've seen. And for D, exactly, we have 3 unpaired electrons for the phosphorus. So, with that being said, how to approach this question. For that first one, if it was S2 2 minus, that is indeed what you would get, because as a rough sketch, you have 2 sulfurs, single bonded, 2, 3, 4, 5, 3, 4, 5, and then you have the 2 minus, so it's going to add 1 more electron on each. So that's how you have S2 2 minus. But other than that, though, that is what we would do for these when they ask for a Lewis structure. It's good to always put that box around it, though, just so that when you have situations where you have this, like the S2 minus and the magnesium, you're pretty much saying, I've drawn it, and the reason why you see nothing there is because it's lost some, or if you see extra, it's because it's gained some. So this is correct. So now for number 19. We want the Lewis structure of the phosphorus tetrachloride compound. They've done the math for us where it says 32 valence electrons, so thank you. And it has P as a central atom, so PCl4 plus Lewis. So as they said, phosphorus is a central atom, so we're going to smack that there. And we have 1, 2, 3, 4. Okay? It's going to be chlorine, 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 chlorine. And now we're going to go ahead and fill in the electrons. So chlorine right now, each chlorine is sharing 1 of its 7. So it's going to be 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. So it's looking like a really good start so far. But phosphorus, on the other hand, is sharing 4 of its 5. So we just have this lone unpaired electron. But, funny enough, we have a plus. The plus means we get rid of an electron. What better electron to get rid of than the lone unpaired electron? So we're going to get rid of that. So if we copied and pasted this, what we would actually have is this. Just like that. Because that lone unpaired electron is now gone. And just as it says it has 32 electrons, we can actually go ahead and count and see if that's the case. So we have 4 bonds, so that's 8 electrons, and then we have 3 times 4 lone pairs. That's 12. 3 times 4 is 12. Ooh, I did my math wrong. So that's 12 times 2, that's 24 electrons, plus another 8, 32. Perfect. And now let's see this formal charge to see where even this positive comes from. So the formal charge for every chlorine, if it wants to be 0, it usually has 3 lone pairs and 1 bond. That will be a 0 formal charge for chlorine. For phosphorus, on the other hand, it's 1 lone pair and 3 bonds. So for it to go from this to now having 4 bonds, it has replaced a lone pair with a bond. When you replace a lone pair with a bond, you go into the more positive direction, which is why this phosphorus is where that positive charge is. So this right here is conveniently the Lewis structure for phosphorus tetrachloride ion. And there you have it. This is what we get. And nonetheless, this is correct. So now we move on to question number 20. So for 20 we have, determine the oxidation number of chlorine in each of these chlorine oxides. So A, B, C, D, E, and we want the oxidation number of chlorine. So A, Cl2O, B, ClO3, C, Cl2O3, D, ClO2, and E, Cl2O5. Okay, so with this being said, the good news is that we all have oxygen there, each of them. And oxygen, the rule is that the oxidation number for oxygen is -2 unless we're dealing with H2O2, which thankfully for us, none of these are. If this is H2O2, it'd be -1 instead of -2. That's the difference there. But nonetheless, all of these are going to be -2. So let's start with Cl2O. I like to write it out a little bit bigger because I like to assign numbers under it. So oxygen is -2. So above it, because there's only one oxygen, we have -2. And for now, the chlorine to balance out the oxygen to where we end up with a neutral atom, or neutral molecule, we need a +2. And if that was the case, we need each chlorine to be +1. That's how I could use the, I guess, the box method. I go like that. Okay? So with that being said, the first chlorine is +1. Next one, Cl(O)3. Same thing, -2, but this time there's 6 of them, so that's -6. So this chlorine side needs to be +6, and that means we have a +6 chlorine. Now for the next one, we have Cl2O3. So similar, we start with the -2 at the bottom, and that means we need -6. So for it to cancel out, we still need a +6, but now there's 2 chlorines, which is how they now distributed between these two, and we get +3. And now Cl(O2). Okay, so now for this one, we have -2 again. That's -4 total. So chlorine needs to be +4. That's the amount they needed on that side. And now for the last one, Cl2O5. Same thing. We have Cl2O5, -2, and that means this will be -10. So this needs to be +10, and that means this has to be +5 for each chlorine. So we have quite a big range of different numbers. Let's see how we did based on our colleague. So they just state the oxidation rules. I just wanted to focus on the one oxidation rule that talks about oxygen. And where is that? The oxidation number of oxygen is -2. Okay, that is what we want. Okay, so that is how we get +1 in the Cl2O. Perfect. In the Cl(O3), we get +6, so that is perfect. The Cl2O3, as they call it, dichlorine trioxide, we get +3. Good so far. In chlorine dioxide, we get +4. So far so good. And for the last one, dichlorine pentoxide, hopefully we get +5, and indeed we do, +5. So with that being said, all of this is correct. So now we finished question 20. We're going to hop into just a little bit of a short intermission just so I can grab some water. I will be right back. Oops, wrong screen. All right, I'm back and I'm ready. So we're gonna hop right back into this and go to question number 21. We want to draw the Lewis structure of O2 2 minus. So for this, oxygen is on the 16th column. Being on the 16th column means that you have 6 valence electrons typically. With that being said, it's going to be 12 electrons we're working with, but we also have the +2 here because there's a 2 minus. So we need to work with 14 electrons. So with that being said, we're going to drop both oxygens in the middle. So O, well, not in the middle, oxygens next to each other, O and O. And now we're going to fill in the current, I guess, valence electrons that each has. So B, 1 is right now being shared. So 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And now we can go ahead and add the 2 minus, okay? And now just go with, as we see, the unpaired electrons. 1, 2. Do we have 14 electrons total? We have 6 lone pairs and 1 bond. That is indeed 14 electrons, so that's perfect. Now, that really would be the Lewis structure of oxygen. To further support this and to see how we got that 2 minus, we can actually talk about its formal charge. Oxygen typically likes to have 2 lone pairs and 2 bonds for it to have a formal charge of 0. In this case, 1 bond was replaced by a lone pair. So when that happens, we take a more negative step, a step towards the negative. So each oxygen here had a minus. So as you can see, because these 2 oxygens both had a formal charge of -1, that is how the whole polyatomic ion has a formal charge, well, not formal, has a charge of -2. And that would be the Lewis structure for O2 2 minus. So there you go, the bond, and then they filled it in, and there you see the 2 formal charges. And that would be O2 2 minus. This is correct. So let's move to question number 22 now. We have balance this equation and it calculate how many grams of lead 2 sulfide form when you use 26.11 grams of lead acetate and an excess / unlimited amount of dihydrogen monosulfate. Or would it be dihydrogen sulfate? Well, nonetheless, let's see what we can do here. So we have, that's a big molecule. PbC2H3O2 2 plus H2S gas turns into lead sulfide, as they said, plus, yeah, we might need more space for this, HC2, H3O2. So the way I like to separate this in order to actually balance this out is that I like to note the parts that I guess come together. We have this, two of them actually, of the C2H3O2, but this only accounts for one of them. So one of the easiest thing we can do actually is just double this. Just add a 2 right there. Okay? And now, with that being said, you're probably wondering, what about the hydrogens? Funny enough, it actually balanced itself out because we had H2S. So just by adding the 2 here, we balance out the whole equation. So we are actually done. And now they're asking us how much lead sulfide forms when we use 26.11 grams of lead acetate, which is what that is, and an excess amount of H2S. So that just says excess. And they want to know how much of this, the lead 2 sulfide. Okay? So with this being said, we need to first go ahead and convert this to moles. Then we do the mole ratio. Luckily for us, it's 1:1. And then we convert that back to grams again. So we need 2 molar masses. The first one is a molar mass of lead acetate. So that would be, count the constituents, 1 lead. And now we have to multiply everything in here by 2. So be wary of that. We would actually have 4 carbon, 6 hydrogen, and 4 oxygen. So it's looking so far to be quite a big molar mass. So we have lead. Lead is all the way here. There we go. 207.2. And don't know why I wrote a 6 there. That should be carbon. 12.011 for carbon, 1.008 for hydrogen, and 15.999 for oxygen. Luckily for us, there's only 1 lead, so that's 207.2. And then the carbon is 4 times 12. That's 48. This is 6.048. And the oxygen, 15.999 times 4, 63.996. Okay? So with that being said, we have 207.2 plus 48.044 plus 6.048 plus that 63.996, and we get in total 325.288 grams per mole. And now for the lead sulfate, we need to now do just 1 lead, okay, and that's 207.2, and 1 sulfur, which is 32.06. So luckily, well, actually not so luckily, these numbers do vary quite a bit, and this would be 32.06, so 207.2 plus 32.06, we get 239.26 grams per mole. Okay, so quite different. So we're going to set up in terms of conversions. We have 26.11 grams, okay, and we want to convert this now to moles. That'd be 325.288 grams per 1 mole of lead acetate. And now, as you can see, based on the formula, for every 1 mole of lead acetate, there is 1 mole of lead sulfate. And then as a last conversion, we have, for every 1 mole of lead sulfate, we have 239.26 grams. And if we cancel our units, we end up with the right grams. So with that being said, that's 26.11 divided by that 325 times that 239.26. And in the end, we get 19.20 grams of the lead sulfide. Okay, that should be what it is, PBS, lead sulfide. So, with that being said, let's see what our colleague got. We have this, and they did balance it out, which is perfect. All they did was add the 2 there, as we did. Okay, and they got the formula here, and they do got the 325.3, which is close to what we got, and they got 239.3, which is close to what we got as well. By doing that and multiplying everything, they got 19.20 grams. Okay, and this is how they got the answer, and that is correct. So with that being said, we've now solved question 22. We're moving on now to 23. So we have a multi-step question. We have first, we want to draw the Lewis structure as F of SF2, showing all lone pair. We want to identify the molecular geometry of SF2. We want to know the hybridization of the central atom. We want to know if SF2 is polar or nonpolar, and the approximate bond angle in SF2. So it's quite loaded. So with that being said, let's go ahead and draw this out. So Lewis first of SF2. So with that being said, sulfur, 16th column, 6 valence electrons. Fluorine, 17th column, 7 valence electrons. There are 2 fluorines here, so they will each contribute 7, so that's 14 total. Plus the sulfur is 6, we are working with 20 electrons. So let's go ahead and draw this out. We have the sulfur, the 2 bonds, and we have the fluorine here, and the fluorine there. So filling out the rest of the valence electrons, it'll be 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, and sulfur is sharing 2 of its 6. So 3, 4, 5, 6. So with that being said, we're almost pretty much close to done. I said the same thing 3 times. Almost pretty much close to. We're close to being finished. Okay, so with that being said, sulfur and the fluorine, how many electrons are we working with here? 2 bonds and 1, 2, 3, 4, 5, 6, 7, 8. 8 lone pairs. So 2 bonds and 8 lone pairs, that's 10 in total. So we have 20 electrons, so that's perfect. What is the formal charge of each? Fluorine, for it to have a formal charge of 0, needs 3 lone pairs and 1 bond, which is what both fluorines are doing. And sulfur likes to have 2 bonds and 2 lone pairs, which is what sulfur is doing as well. So this is also balanced with all formal charges of 0. Okay, so now for the last part, I think that covers it for this. So we've done the Lewis structure for this, so we're good to go. Okay, so now with that being said, it says identify the molecular geometry. For this, I would actually like to identify the electron geometry, which also let us know the hybridization as well. Okay, so with that being said, we would have 4 pairs in total, which breaks down to 2 bonding pairs and 2 lone pairs. But the 4 pairs in total tells us that the sulfur is sp3 hybridized, and this is a tetrahedral electron geometry, okay? But at least we found the hybridization, sp3, okay? And now they're asking the molecular geometry. Because there is 2 lone pairs and 2 bond pairs, we can actually say the molecular geometry is bent. What do I mean? Is just like oxygen, this is what sulfur would look like. Okay, if I could draw better, I'd show you. There we go. Close enough. Something like this. This is the bent structure they're referring to, okay? So now we've answered the molecular geometry part, okay? And now it's asking us if its molecule is polar or nonpolar. For this, we actually have to refer to the periodic table and look at the electronegativity difference. The reason why is because it's not just a linear interaction. As you can see, the fluorines are now pulling unevenly on the sulfur. So we need to know the electronegativity difference to see if the pulling force is actually something considerable to add. So fluorine, unfortunately, is the strongest, as we know of, electronegative atom. So most things bond to fluorine end up being a polar bond. But sulfur is sitting at 2.58 versus a 3.98. So without even doing the math, I know this is above 0.4. These are polar bonds. And because it's an uneven distribution, as you can see, due to the lone pairs at the top, we have a net movement downwards. Okay? That's what's going to happen because the fluorine is going to be pulling here and this fluorine is going to be pulling there. But overall, it's going to be moving downwards because it's going to be going towards the side that's more electronegative. So that being said, is it polar or nonpolar? This is going to be polar. And now for the last question, it's asking us what is the approximate bond angle of SF2? So now this is where the electrons kind of play in, the lone pairs on the sulfur, because just like with the oxygen, tetrahedrals, their perfect bond angle is 109.5 degrees, okay? That is when everything is around the same and they have, like think of methane, for example, CH4. That is a perfect distance between each other to where they're as far apart as possible. When it comes to now including electrons in it though, it kind of squeezes things together, okay? So with that being said, in this case, the bond angle approximately would be less than 109.5. I cannot say anything further than that. I just know that it would be less because they're being slightly squeezed together. Okay? So now let's review if we have answered to every part of this question. We do have the Lewis structure. We have the molecular geometry, bent. It's sp3 hybridized for the sulfur because there's 4 groups. It is polar, and the approximate bond angle is less than 109.5. So there we go. They drew it as a bent form. So this is a good start. Molecular geometry is bent. Perfect. Hybridization is sp3. We are doing good so far. Polarity, it is polar in nature because sulfur and fluorine atoms differ in the electronegativity. Perfect. And now for the last part, bond angle, slightly less than 109.5 degrees. So they actually gave us the actual bond angle, which I'm surprised about. Most of the times we just know that it's less. Because a lot of things, like even for example, H2O, water, we just say it's less. There's probably empirical data that shows the actual bond angle, but based on the relationships that we've seen from other bent molecules, we can typically say that yes, this will be less than the standard 109.5 degrees. So that being said, this is correct for question number 23. Now question number 24. We have, draw the Lewis structure for methylamine. Methylamine molecules have one amino group. be certain to include any lone pairs. So they give us CH5N, and it's called methylamine. And they want us to draw the Lewis structure for this. So this one is tricky because you have to know what they mean by an amine group, okay? And in this case, an amine group is typically, if I recall correctly, this is poorly drawn. Trying to figure out the best way to do this there. This would be the amine group, okay? Just like that. Because that is what would attach to the rest of it. Alright? So nitrogen and 2 hydrogens. That is what they mean by an amine group. Well, amino group, sorry. With that being said, let's go ahead and try to approach this like your typical, I guess, Lewis structure, but just with this information now added. Okay, this will affect how we draw it. So carbon, being on the 14th column, has indeed 4 valence electrons. Hydrogen, 1 each, being on the first column. So that's 5. So that's 4 plus 5 right now. And then the nitrogen is another 5. So we're dealing with 14 electrons total. So let's go ahead and draw it out. So based on the information we were given, we have C and N. Those two are going to be in the middle. And then we have pen technical difficulties again. I do believe it's time for me to change the battery, so that's what I will do after this lesson. So hopefully now I can write. Yes, indeed. So we have H, 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 H. There we go. 5 H's. And then we have to review this. So right now, hydrogens are just sharing one of its 1. Carbon right now is sharing 4 of its 4 electrons. But the nitrogen right now is sharing 3 of its 5. So we have 4 and 5, which is coincidentally what I drew here as the amino group. So with that being said, we have 14 electrons, 1 lone pair, and 6 bonds. That does add up to 14. Perfect. And now does this have the correct formal charges? Let's find out. We have, just to make sure, trying to think, hydrogen, formal charges of 0 will just look like that, 1 bond. Carbon's formal charge of 0 is just 4 bonds. Nitrogen's formal charge of 0 is 1 lone pair and 3 bonds. So funny enough, everything here has a formal charge of 0. So this, because they also follow the octet rule based on the carbon and the nitrogen, would be the Lewis structure for methylamine. And we did include the lone pair, which is only on the nitrogen. Okay? And as I said, the only reason I was able to draw this and not just something that's like, it would be a very stressful time to figure out how to put all the hydrogens and nitrogen on just a carbon, which is why it's good to recognize your groups. And funny enough, this ties into knowing your naming. I know there's a word for it. I blanked out, but just call it naming. This is why it's important to know your naming rules. So that IUPAC naming rules. There we go. So that way, when they give you things like this, you can even recognize methyl or methane, which is known as just CH4. And if you have methyl and amine, or at least 1 methyl and 1 amino group, you just slide that nitrogen there, and you'd have still gotten the same answer because you knew what pieces you were working with. So that's why it's just important to get familiar with your naming and such, so these questions become easier to solve. Okay? And there you have it. There's that lone pair. And that indeed is the amino group as I drew up there. So this is correct. So now we're going on to question number 25. For this we have KNO3 is mixed with water. Is the solution basic or acidic? And then they ask, is ClO a weak acid or base when mixed with water? So for this, these are a little bit tricky, I won't deny, because for this we have to really know what they split into. So let's start with, so A is KNO3 and B is ClO minus. Okay? So we have, if we just draw the form, we have K plus, well, KNO3 mixed with water. We're going to do a substitution. That's what we're going to aim for. So I'm actually going to write this as HOH, because that turns into KOH plus HNO3. That is the first one. Second one, we have ClO minus plus HOH. We have typically HClO plus OH minus. Okay? So with that being said, this is where it gets tricky. This part, frankly, I don't think it's as easy to memorize, but the best thing I would memorize would be a list of strong acids and bases. And if you don't see them, then, if you don't see that in your products, then you know you're working with weak acids or bases. So that being said, we have KOH. Anything with hydroxide typically is already a strong strong base. So we can kind of ignore this, okay? Because strong base means that even though I've written KOH there, potassium has literally no business wanting to be with the hydroxide again. That's what it means to be a strong base. It dissociates completely, aka even if they're flowing in the same water, potassiums and hydroxides, they will not rebond together. They'll rather stay separate. And now HNO3. Nitric acid, unfortunately, barely passes the bar for a strong acid. So this as well, no interaction. The hydrogens will like to be by themselves, and the nitrates will just float by themselves as well. So I crossed them out because that's all we have. All we have is strong acid and bases. And when you have that, funny enough, the solution would be neutral. So they didn't even give that option, but that is an option you can go for. The solution will remain neutral because these salts, the KNO3, well, not just these salts, I guess this one salt, KNO3, is made from a quote-unquote strong acid and strong base, as I've shown here. So because of that, this salt will not want to interact anyway with the water to make it acidic or basic, because they're never even interacting in the first place. So that is why this would actually end up being neutral. And so to clarify, if you see that the quote-unquote products, as I drew this formula, is just going to be a strong acid and a strong base, if you don't see anything weak there, it means that it's not going to happen, if that makes sense. Because KOH would never be a product that you'd see, because the potassium and the hydroxide don't want to interact. Same thing with the HNO3. And because that is happening, you know that you have a neutral salt. So with the next question, is ClO a weak acid or base? So referring back to our list, we have ClO, or at least HClO is not, at least from what I can see, that would be like hypochlorous acid. There it is. This is a weak acid. So there is interaction there. If you put ClO, ClO minus, it would actually go with the water and try to take some of the hydrogens from it, forming this base. So that makes this the base. This would be the acid, and this would be the conjugate acid, and this would be conjugate base. So specifically referring to the ClO minus, when they ask if it's a weak acid or a base, as you can see here, the answer, this would be a weak base. Okay, so now with that being said, these are the answers for it. I'm going to refer to my colleagues so they can actually elaborate more on the whole KNO3 situation, just to be able to pick out some keywords in case my explanation did not make sense. So, KOH, as they did it, they actually did the reverse formula to make it shown a little bit easier. KOH is a strong base, and HNO3 is a strong acid. So salts of strong bases and strong acids, the pH will remain neutral at 7. Think of it as a neutralization reaction where they just cancel each other out. Okay? Based on these rules, KNO3 is not an acid or base because the solution of KNO3 dissolved in water would be neutral because it's from a salt of a strong base and strong acid. Okay? So now with that being said, NaClO is a salt which dissolves in water to give us the ClO minus that we're looking for. Okay? So if ClO minus works with acid, it will be HClO4 minus or plus OH, which is what we got here. Okay? But it says here that ClO is a strong acid mixed in water, which may be a fair mistake, but it is a mistake nonetheless, because as we see, we have different ones. We have perchloric acid, which is a strong acid. We have hydrochloric acid, which is a strong acid. And we have chloric acid, which is also a strong acid. But hypochlorous acid, which is all the way down, as I saw before, but I've now lost it here. And this is a weak acid, because that's what we have here as ClO minus. And you know it's a weak acid because it has a Ka value, dissociation constant, that's less than 1. Okay? So with that being said, this unfortunately is wrong. And not only is it wrong in the acids and bases, it actually is wrong in regards to it is a weak base, not even a strong acid. I think they just got it switched around somehow, because they say that this is a weak acid. Hypochlorite is a conjugate base of the weak acid HClO. So when you're a conjugate base of a weak acid, you're also most likely a weak base, because if you don't dissociate completely to one side, if I added the opposite, it also wouldn't dissociate completely to the other, or resociate completely to the other side. So typically a weak acid's conjugate is also going to be a weak base. Okay? It's just going to be relative, I guess. This is where it gets a little bit tricky. A weak acid that's close to being a strong acid will have a conjugate of a weak base that's extremely weak. So if I were to like draw a chart, the stronger the acid, the, I guess, weaker the base, if that makes sense. It's a little bit hard to draw because, yeah, it's very hard to draw. But yes, I would just stick with weak acid will lead to a weak base. So this is incorrect. ClO minus is a weak base. What you can see here on the acids and bases sheet, okay, if we did, where is it? Lost it again. Hypochlorous, there we go. We can actually just use this. The pKa is 7.46/7.53. So the pKb will be 14 minus that. Let's use the one that's even more basic. 14 minus 7.53. That's like an extremely weak acid. Almost, you could argue that it's basic almost. But nonetheless, we have 6.47. So if I did now the 10 to the power of negative that answer, our KB is sitting around 3.39 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 times 10 to the negative 7. Okay? Because that KB value is still less than 1, it's still going to be considered a weak base. So with that being said, that was incorrect, And we can now move on to question number 26. We have the answer. The question is asking, what is the Lewis structure of C2F2? And they actually were nice enough to give us a structure of FCCF. But even if they didn't give us that, I'm sure we'll be able to figure it out. So, first thing we have is the carbons, which are the 14th column electron elements. So they have 4 valence electrons. The fluorine on the 17th column has 7 valence electrons. So that would be, just to make sure I'm thinking thoroughly this, we have, we have 8 from here and 14 from here. So it's going to be 22 electrons total we're working with. So with that being said, we have C, C, F, and F, okay? What we can do here is that we fill in the valence electrons each had. 1, 2, 3, 4, 5, 6 of the 7 it has, because the 7th one is being shared. Same thing here. We'll now count the 1 in that bond. So 2, 3, 4, 5, 6, 7. Just so it makes it a little more clear. And the carbons, on the other hand, are each sharing 2 of its 4. So 3, 4, 3, 4. In order to get the picture, as you can see, we have to take care of these unpaired electrons. How do we do that? By throwing them in to form 2 more bonds. And that is how we get the picture of this. So everything else stays the same. And now we have a triple bond between the carbons. And now if we wanted to make sure that the formal charges were good, fluorine likes to have 3 lone pairs and 1 bond, which is what this fluorine has. That connotes a formal charge of 0 for the fluorine. Carbons, its formal charge of 0 is 4 bonds, which it also does have, because a triple bond just counts as 3 bonds. So with that being said, this whole thing is a formal charge of 0. That's why it has no charge, in total the net charge, and that's what we get for the Lewis structure. And do we have 22 electrons? Considering we have 6 lone pairs and 5 bonds, I would say yes, we do indeed have 22 electrons. So this is correct. So now question number 27. Okay. We have, what is the systematic name? Oh, interesting. For MgF2. So name for MgF2. So with this, we have to refer to our periodic table, and the first thing we have to note is whether this thing is an ionic or a covalent compound. We have magnesium, which is the Mg, and we have fluorine. So luckily for us, according to the periodic table, magnesium is indeed a metal, and fluorine is indeed a non-metal. So I'll put that in red, actually. Okay? So there is a distinguishable difference. This is an ionic molecule. Now, in terms of the naming, how we go about naming this is that we have to make sure we change the end of fluorine. But other than that, because it's an ionic molecule, we factored in already the different charges. We don't need to state how many fluorines we have. It would literally be the only change. It would go from fluorine to fluoride. That's it. It'd be magnesium, fluoride. That would be the only change that we have to do, because that is how you would name ionic molecules. So let's see what our colleague did. They do state it's an ionic compound, so it should follow the nomenclature. That's what I'm looking for ionic compounds. Mg, magnesium. Alright. And then anion, we have, well, we don't know yet, but we can just put magnesium, and on the anion is fluorine, and we replace it to say fluoride, and we put them together, it ends up being magnesium fluoride. So this is correct, and that would be our answer for this question. So now let's go to question number 28. We have, how many valence electrons are there in the atom of arsenic? So arsenic valence electrons. Well, not sure if you can read it, but let's go to the periodic table and see what arsenic is. Arsenic is indeed on the 15th column, okay? And when you're on the 15th column, typically you can just say right there you have 5 valence electrons. But there's other ways you can show this as well, specifically the electron configuration. I'm going to go ahead and use a shorthand notation because arsenic is the 33rd element. We're going to refer to, so we use shorthand notation, be argon as what we start with, and that would now be 4s2, okay, 3d10, 4p3. And now you will see that arsenic being the 33rd element, because argon accounts for 18 of them in terms of the superscripts. We have 18 plus 2 plus 10 plus 3. We do indeed get 33. Now, what does this mean, and how do we find the valence electrons from this? Let's look closer. So valence electrons are in the outermost shell. The 4s represent the 4th, orbital or 4th shell we're working on. That is the biggest number, so this is our outermost shell. The 2 and 3 represent how many electrons are in each orbital of the outermost shell. So we have 2 electrons here and 3 electrons in the p orbital. So together, this also supports that we have 5 valence electrons. So there's 2 ways to find this answer. One is by just going through the periodic table and seeing that it's in the 15th column, so that's 5 valence right there. The other way, as I've just shown, is just going through the electron configuration and seeing based on the most outer shell how many electrons are there, which will be the 4s. So this is correct because I did see that it has 5 valence electrons. So now let's go on to the next question, question number 29. We have, what is the formula for the conjugate base of NH4? You get base, and we also want B, the conjugate acid of C2H3O2 minus. So for this, in order for me to get a conjugate base of NH4+, I need to get rid of a proton. So I need to mix this with a base. I need to make water serve as a base. So I have NH4 plus H2O. And remember, this is our acid and this is our base. So what's going to happen here is that I want to donate a proton to that water. So I will now have NH3 plus H3O plus. This right here will be the conjugate base, which is how I was looking for, and this will be the conjugate acid of water. So this being said, the formula for the conjugate base of ammonium ions is funnily ammonia NH3. So this is for A, or 1. And now for the next one we have C2H3O2 minus. And I do believe this is like acetate ion, I'm pretty sure. Nonetheless, we have plus water again, but this time we want this to serve as a base so we can get its conjugate acid. So we have a reactant with water, and we get sorry, I forgot the minus, HC2 H3O2, which is, I think, is known as acetic acid, plus OH minus. As you can see, the minus has just gone somewhere else. Just like in the first question, the positive had went somewhere else. So this would be the conjugate acid, and this would be the conjugate base. And because they asked for conjugate acid, for B, we can say that yes, the conjugate acid is HC2H3O2. So there you have it, the conjugate base and conjugate acid of these. Okay? And now, let's see what our colleague got. They got NH3, perfect ammonia as a conjugate base, and C2H4O2, or just HC2H3O2. Same thing, that would be the conjugate acid in this case. So this is correct. And now for the last question of the evening, we have determine whether CF2Cl2 is polar or nonpolar. Which of the following hybridization schemes allows the central atom to form more than 4 bonds? So with that being said, I'm not sure if you can read the answer already, but we're going to just solve A and B. So CF2Cl2, polar versus non-polar. So with this, what we have is, if you want to go ahead, so I want to write down both questions first. And which is more than 4 bonds? That is, as I said, sp3, sp3d, and sp2. Okay? So first part, we want to draw the Lewis structure of CF2Cl2. Okay? Carbon, being on the 14th column, has 4 valence electrons. Fluorine and chlorine, being on the 17th column, each have 7 valence electrons. So that's 7 times 4, 28, plus that 4 from the carbon. We're working with 32 electrons. So, with that being said, put the carbon in the middle. F, F, Cl, Cl, and then we fill out the valence. So fluorine was sharing 1 of its 7, which is why we can add 6 more. Same thing here, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. Definitely almost missed one here on the fluorine. Okay, and then 2, 3, 4, 5, 6, 7. And carbon is already sharing 4 of its 4. Do we have 32 electrons here? Let's see. We have 3 times 4 lone pairs, and we have 4 bonds. So that's 12 plus 4, that's 16 total bond slash lone pairs. So that is indeed 32 electrons. So, with that being said, do they follow the octet rule? That I can also say for sure that is true. And do all these have a formal charge of 0? Let's find out. Fluorine's formal charge is 3 lone pairs and 1 bond, which is what it's doing. Same thing with the chlorine, is 3 lone pairs and 1 bond. And for the carbon, for it to be 0, is just 4 bonds. So all of these fit the criteria of all having a formal charge of 0. So that's the Lewis structure. Now to know if this is polar or non-polar, actually, it would be best to draw this as its molecular geometry. Because what if I drew this like this? Now, you could argue that, wait a minute, the fluorines are pulling evenly and the chlorines are pulling evenly, so this will cancel out, which is why you need your molecular geometry. So this shape is known as tetrahedral. Okay? And what this would actually look like, if I drew it out to my best capabilities, something like this. And it doesn't even matter what I even put here anymore, because as you see, this is always going to be uneven. There's no way the fluorines and the chlorines could pull to where they would quote unquote cancel each other out. And that's actually what I want to stress, because, so to clarify, as you can see, that bolded line is imagine the chlorine coming out of the page, and that dashed line, imagine the chlorine going into the page. So that's what I mean by there's no really good way to draw it to where it balances out. And the reason why I mentioned this is because if you go to the periodic table, fluorine is like the strongest, one of these, if not the strongest electronegative atom at 3.98. The difference between fluorine and carbon, in fact between fluorine and chlorine, because that's really what's competing, that's 3.98 minus 3.16. So like a 0.82 difference around there. Point being that this is enough for us to say that these are going to be polar, not really polar bonds, but there's a big enough difference to where fluorine would have a higher affinity for the electrons than the chlorines. So overall, you'd see like a net, I guess, if I were to able to draw it, kind of like a net pull this way towards the fluorines, okay? And because exactly these fluorines can't bounce out, that's how we get this shape. Well, I mean, not this shape, but this kind of pull. And because there is a pull, you can now see for sure that this is going to be polar. And that's why drawing the Lewis structure was not enough, because had I just left it at the Lewis structure, exactly, I could argue that the fluorines are perfectly cancel each other out. Now that you see the molecular geometry, it should be a little bit more clear to be like, okay, well, now I know this wouldn't work. So now the next part is asking which of these is more than 4 bonds: sp3, sp3d, and sp2. So for this, we need to know what that even means, okay? So this would be an s orbital, this would be a p orbital, this would be a d orbital, okay? And we're only messing with the there we go. Oh, I think I minimized. That's what happened. We're only messing with the first d orbital. So we're going this far, according to the question. So, s, p, and d. In each orbital, it can fit 2 electrons. Okay? And now we're going to apply this to, I guess, like real life. If I said I had sp3, how many electrons am I working with? In total, 8. 8 shared electrons with me, or just 8 electrons I have. Funny enough, looking at the central atom, that carbon, this is what we actually would refer to as being sp3 hybridized. And as you can see here, only 4 bonds, which is why this would not work. sp2, 6 electrons. We're thinking of things more like this. Definitely blanked out there for a second. Like boron. Okay? That is what we're thinking when we're thinking of sp2. It does get more complicated than this. Other things can count as sp2, but this is what I want you to visualize when you think of sp2, because there's 6 electrons that can fit. But now sp3d, we're dealing with the first orbital there. All of a sudden, we're dealing with 10 electrons. For this, think of it like phosphate, because that one can break the octet rule. This right here is what comes to my mind when I think of sp3d, because we need 10 electrons that is sharing or just has to itself. So with that being said, the only one that has more than 4 bonds, that can have more than 4 bonds, would be the sp3d orbital. That will be the one, okay? Not the sp3 and not the sp2. So with that, let's see what they says. It's like sp3d allows it to form more than 4 bonds because it typically has 5 bonds. Something else you could also do is like with sulfur, this is also technically sp3d, okay? Now, with all that being said, as we reviewed, CF2Cl2 is the polar molecule according to my colleague as well. So with that, we are good to go. So we fully answered this question, okay? So this is correct. Let's see, do we have anything else? I don't think we should. Let's find out. Okay, so it looks like we're done. And with that being said, I just want to thank you again for joining me this stream. If you have any questions or want to go over the topics that was covered today, please reach out at the link in the description below. Once again, thank you for joining this stream. You have a lovely rest of your evening, and see you next time.